Here's what we already know. We already know that if the eigenvalues are real, we have real eigenvalues. There are three possibilities. It's starting to die again. So, right, if they're both positive, you have the situation where everything shoots outwards, right? You have some sort of eigenlines that look like this. Maybe like that. Whoops, this goes to the origin. And then everything else is right, like all the arrows are all going away. And we call that a source or a unstable node. On the other hand, if they're both just negative, and so I want to point out, well, no, I'll point that in a minute. So if they're both negative, everything is pointing inwards. So, right, these our eigenlines could be any kind of lines, but right, I'm just kind of drawing them very generically. And so then everything, right, everything is pointing inwards. So right, if you started like somewhere like here, you might do something like that. Or if you started somewhere here, you might do something like that. Right? It's not, and again, I'm not 100% exactly how it looks. We call this a sink or a stable node. And then, yeah, totally, Lindsay, for sure. And then finally, when you have opposite eigenvalues, so lambda, it doesn't matter which is which, right? One of them is negative, one of them is positive. That's when you have, right, one thing going inward. Right, that's the negative one. So that's the eigenline for lambda 1, and another thing going outward. That's the eigenline for lambda 2. So in this case, right, you have a saddle, which is unstable. So you have things going like that, that, right? Okay. Yes, we'll definitely get to doing eigenvectors of complex. But before we do that, let's go ahead and talk about what the solutions look like. So they're all going to be spirals if the eigenvalues are complex. And there's a connection I want to make for you that I think is definitely worth trying to retain. So here's what we've got. So let's say, our complex eigenvalues have a real part and an imaginary part, and they always come in complex conjugate pairs. Meaning, if you have eigenvalues that are complex, they're always going to look like lambda 1 and lambda 2 are going to be equal to A, which is the real part, plus or minus B times I, which is the imaginary part. So, red here, right? This number here is the real part. This number here is the imaginary part. And what's kind of cool is we have similar stability criteria, right? Over here, when the eigenvalues are both positive, we have instability, right? Because things grow really, really big as time goes on. Over here, when the real part is positive, we're going to have instability. So here's what this is going to look like. So if the real part is positive, then we're going to have an unstable spiral, which is going to do something like, I don't know, if we start like here. Now, I will point, I know he said this in class, and I think this is a good thing to say, we can't draw the eigenvectors or the eigenlines in the phase plane, right? Because this is both x and y being real. This isn't the complex plane. So, right, for real eigenvalues and real eigenvectors, you can totally draw them. You can draw the eigenlines in the complex plane, you cannot. So what we have here is that when you start somewhere like here, and we'll talk about how to determine if it's going clockwise or counterclockwise. So no, they're the same thing. So if you look at Maxwell, if you look at the program, so there's actually two programs you can download, D field and P plane. The phase plane is specifically for a system of two linear differential, or two differential equations. They don't have to be linear. So it's a system of two differential equations, right? dx1 dt equals something, dx2 dt equals something. Whereas the direction field, if you think back to 17b, we were doing things like we were using the direction field to plot the dy, something like dy dx equals x plus y, right? Where you still would like pick a point 1, 1, and then you would see what the direction was. Whereas in the phase plane, right, you're doing the same sort of thing, but you have to look at both what dx1 dt is and dx2 dt is to figure out which, right? dx1 tells you which way you're going in the x direction. dx2 tells you which way you're going, what way you're going in the y direction. Whereas if you have dy dx, you're just saying, oh, I know the slope as y is changing as x, right? So it's a little bit different, but people still call the phase plane the direction field, right? Because you're still graphing stuff, you're still plotting all those little direction vectors. Okay, so if a is greater than 0, you're going to have an unstable spiral, and you start at some initial condition, it's just going to like spiral outwards. So unstable spiral. And the reason for that, right, is because if you have, so we're going to get a little complicated here, not too complicated. We know that that our solution, and we'll say more about this in a minute, that our solution looks something like x of t as a vector, meaning that's x1 and x2, is equal to c1e to the lambda 1, which is going to be a plus bi times t times the first eigenvector, and so on and so forth. And what's happening here, and he said this in class, but I'm going to say it again, right? E to the a plus bi times t. I'm going to rewrite that as c1 times e to the a times, e to the a t, apologies, times e to the bi t, or I'm probably going to write it as ibt actually. Times v1 plus similar thing for the second eigenvalue. But e to the I times a number, that's the whole Euler's formula thing, where this is equal to e to the I times something is cosine of that something plus I times sine of that something. Cosine of bt plus I sine of bt. v1 plus that, that. So here's what's happening as time goes on. As time goes on, this part's getting bigger and bigger and bigger, right? So as time goes on, both your x and your y values are getting larger, but this is making it oscillate. So you're kind of like, we're getting bigger, but then we got like, so you're kind of doing this thing where you're going back and forth, right? So if you were going to try and graph x and y versus time, right? So here is time, x, maybe x, you know, like, so if we start like here, which maybe that's the point, I don't know, x is 1 and y is, they both kind of look like they're 1. So if we start both x and y at 1, they're both kind of just going to oscillate. So, right, and it looks like, x gets smaller first, right? So x gets smaller, smaller, and then right about there it starts getting bigger and bigger and bigger. So, right, so this is the graph of x gets smaller, and then it gets bigger and then smaller, but every time, right, the amplitude is growing because this is getting bigger and bigger and bigger. And y would be doing something similar, except if you start here, y actually gets a little bit bigger at first. So y gets a little bit bigger, but then you get smaller and then bigger, and then, right, it's that whole kind of thing there. So that's why we have this spiral. That's I mean, I guess you could kind of say like, this is why you have that spiral shape. Because if you look at this formula here for x and y, for the vector x of t, which is x and y, right, you're seeing that you have this oscillatory nature. Right, where as time goes on, this is going to oscillate between like 1 and -1. It's oscillate between 1 and -1. So I don't want to get super deep into that, but that's the idea. That's why when you have a complex eigenvalue, you're always going to get a spiral. Okay, I'm going to erase all this. So the other two possibilities are, if the real part is negative, you have a stable spiral. So if you start somewhere like out here, you're going to spiral inwards until you get to like the origin. My spiral does not look great. Right, and I've drawn both of mine that happen to be going counterclockwise, but there's no reason to think it couldn't go the other way. So this is right. This is going to oscillate and dampen. And this one, so if a is greater than 0, this e to the at thing gets really, really big. So you oscillate, but you get big. But if a is negative, this e to the at thing is going to get really, really small, right? It's going to converge to 0 as time goes on. So this is going to be a stable spiral. And then the weirdest one is when you don't have a real part. So if a is 0 and it's purely imaginary, then you're going to have what's called a center, I believe. I think that's what it's called. Let me double check. Yeah, or a neutral spiral. So what's kind of crazy about this one is wherever you start, you're going to end up exactly back where you started. And the reason for that is because if this part is 0, then you're just left with the vector being cosine of bt plus I sine of bt. But here's what's going to happen. As time goes on, you're going to get back to the same angle, right? Like if t is 0, you're going to cosine of 0 plus I sine of 0. Okay. But then if you go all the way around to where this is 2 pi, you're back at the same angle, which means you're back at the same value for x and for y. Because nothing has changed, because there's nothing here to make it bigger or smaller. So hopefully that gives you a tiny bit of insight into what's going on here. So we have 6 things. Eigenvalues both be positive, unstable. Or if it's complex, the real part can be positive and it's an unstable spiral. But I want to point out the real thing being unstable, whether it's complex or just real, means instability. On the same note, if the eigenvalues are both negative, or if the eigenvalues both have a real part that's negative and they're complex, you have stability. Everything's going to get closer and closer to the origin. If they're complex, it's a spiral, a stable spiral. If it's just real, it's a stable node. And then the last 2 cases don't really relate to each other. Right? If the lambdas are opposite signs, you have a saddle. And if there is no real part in a complex eigenvalue, you have a center. These are the 6 things that can happen. Okay, so let's talk about, let's talk about this next example. So in this next example, we will definitely talk about the eigenvalues and the eigenvectors. Most of the time, at least in the past, I have not seen people get asked very much about finding what's under the word saddle? The thing I just erased? Yeah, sorry about that, Jim. What was under the word saddle? Anybody remember? I mean, we could go look at the video later and tell you. Yeah, I don't remember what I had under the word saddle. Oh yeah, saddle's unstable. Thank you, Ethan. Appreciate it. Yes, the saddle is unstable. Good call. So let's look at this solution, this system. I want to classify the stability of the following system. Of the system given by a equal to, what do we got here? 2, -5, 2, 1. Okay, now something I want to stress, because I definitely have people asking me about this in office hours. When they give you just the matrix, they expect you to know what that means, right? If they're giving you this matrix, what they're really giving you without writing it down is that dx dt equals 2x minus 5y and dy dt equals 2x plus y. Right, so you need to be very, very comfortable by saying, oh, I've got a matrix. It means I have this system of linear differential equations. Okay, make sure you're cool with that. It is vital. So I want to find the eigenvalues. And I'm going to use the trace determinant method because I still think it's a good way to do it. So my trace is 2 plus 1 my determinant is 2 times 1 minus negative 5 times 2. That's going to be 2 plus 10, which is 12. So then the eigenvalues are going to be the trace plus or minus the square root of the trace squared minus 4 times the determinant all over 2. And simplifying this a little bit, let's see, this is 9 minus 48. 9 minus 48 is negative 39. So I've got 3 plus or minus the square root of 39, sorry, negative 39 all over 2. And we should write that as 3 plus or minus I times the square root of 39 all over 2. Typically, when you're writing the I, you typically write it after constants, but usually in front of square roots, even though those are also constants, because it's easy to actually make it look like the I is inside the square root. That's a good question, Max. Is there an advantage to doing it this way versus the other way? Well, let's do it the other way and see. So I will say, yes, there's an advantage. And the advantage is that there's actually a way of saying, if you know that the trace and the determinant are a certain way, you can just say what the solution is right off of that. And actually, I will show you this graphic really quickly because I think it's worth, again, right? I know he's not focusing on this, so I don't want you to spend like too much thought, right? It's like how much thought process do we want to dedicate to something he's not really covering that much in class, but it's still a totally valid and useful way of doing it? I don't have a good answer to that question, but what I can show you is, where'd you go? It's in section 10.2, I believe, right before you get to the problems. Let's see, 1 second here. Come on, section 10.2. Yeah, there we are. So, and I'll talk about this more if you guys want me to, but I won't if you don't. So let me share my screen real quick. So this graphic here, if you plot the trace on the x-axis and the determinant on the y-axis, this tells you that if your determinant is negative, you have a Saturn. If your determinant is positive, well, a lot more things can happen. So if your determinant is positive and your trace is positive, you have unstable things. You either have an unstable node or an unstable spiral, depending on whether the determinant is bigger than 1/4 of the trace squared or whether it's smaller. And then if the trace is negative, you either have a stable spiral or a stable node. So I can look at a matrix, and I think we're going to be doing, I really feel like this is worth our time because this does start to come up later when we have systems that are not linear. So I do think I'm going to talk about this a little bit because I think it's worthwhile looking towards the future of this class. But I can see looking at this trace being 3 and this determinant being 12, well, my determinant's positive, so I know I'm up above, and my trace is also positive, so I know I'm to the right. So I know I'm up in this first quadrant here. So I either have an unstable node or an unstable spiral. And the way I know which it is the question is, am I above this parabola or below it? So is my determinant, let me just use the symbols, is my determinant greater than 1/4 of the trace squared, or is it less? Basically, this question here, sorry, let me stop sharing. This question here is asking, do we have a complex or not eigenvalues, right? Because again, this formula is the trace plus or minus the square root of the trace squared minus 4 delta all over 2. So if your determinant is bigger than 1/4 the trace squared, then this is going to be negative, and you're going to get a spiral. If your determinant is less than 1/4 the trace squared but still positive, you're going to get a node. So I do think it's worth our while, but let's talk about, yes, I think it's worth doing it this way. But if we did it the other way, it would also work just fine. The thing about doing it the other way, I mean, it's the same work, it's just different, right? If I did the determinant of a minus lambda I, so that's going to be 2, -5, 2, 1. So 2 -5 to 1. If I did the determinant of that and got 2 minus lambda times 1 minus lambda minus -5 times 2, this ends up being lambda squared minus lambda minus 2 lambda is minus 3 lambda, and then plus 2 plus 10 is plus 12. You're still getting to the same quadratic formula, right? Your answer here is going to be lambda equals -3 plus or minus the square root of -3 squared minus 4 times 1 times 12 all over 2 times 1. Literally the same thing we have right here. So I don't have a great answer for you, Max, other than I think it's worthwhile. Occasionally it feels nicer. I don't know. But let's go ahead and continue with this example because I want to say what we have. So we know that our eigenvalues are 3/2, right? 3 divided by 2 plus or minus I times the square root of 39 over 2. So our eigenvalues are complex. Do we have a spiral or a node? Definitely a spiral. Okay, the real part's positive. Is it unstable or stable? Well, we know when the eigenvalues are positive or when the real part's positive, it's going to be unstable, right? So we have an unstable spiral. Okay, the last, well, not the last, but the next thing I want to answer is which way does it rotate? So is it rotating clockwise or counterclockwise? Well, there's an easy way to figure this out. Semi-easy. So if you have a spiral, so you have to start with having a spiral first of all. If you have a spiral, you can just say, I'm going to plug in some points here and see what's happening. So I can say, well, at, say, for example, at the point 1, 0, dx dt would be 2 minus 0, and dy dt would be 2 plus 0. So at the point 1, 0, I'm going up and to the right. So if I was going to graph this thing, right, I'm going kind of, right, if that's the point 1, 0, I'm going this way. So it looks like I'm probably going to be, well, that's not, I feel like I like the point 1, 1 better personally. This feels like I could end up going, no, I don't think I could go that way, right? Because you kind of have to, I don't know. Let's plot another point. Let's plot the point, say 0, 1. So 0, 1, I get dx dt equal to -5 and dy dt equal to 1. So I'm going left and up. More left than up. So I'm kind of going like that. So to me, this is looking like we're definitely going to be going, counterclockwise. Now, here's the thing that I found somewhere, because I was like, how do you know this, like, without drawing it? Well, there is a way, there is a condition on the matrix, and here's what it says. If you have a spiral, then look back at your matrix. And if this one right here, so if the spot in the upper right-hand corner, if that is negative, it's going to go counterclockwise. And if that is positive, it's going to go clockwise. Now, I don't think that would be a very good answer if someone asked you on a test, I know this thing about the matrix. I think they would want you to do something like this and be like, okay, I'm going to draw a couple of arrows to see which way it's kind of looking like it's going. But it is true that if you have a spiral and it's negative there, it's going to go counterclockwise. If it's positive there, it's going to go clockwise. End of story. Okay. So let's continue on with this and let's find the eigenvectors. Now, this is probably something you're not going to have to do very often, but you might have to do occasionally. So let's find the eigenvectors. It's not going to be pretty. It's almost never going to be pretty finding the eigenvectors for complex eigenvalues. So here's our eigenvalues. Lambda 1 is, I'm going to always make lambda 1 be the one that's plus. So lambda 1 is going to be, let's write it like this. 3 plus I root 39 over 2. Let's have lambda 2 be 3 minus I root 39 all And this might be one instance where it's better to do it the a minus lambda I times the vector equal to 0. So we'll try both ways then. So we're going to try doing it by doing ax equals lambda x, and then we'll also try it by doing a minus lambda I times x equal to 0. We'll do that for the second one. So for the first one, my matrix, not my vector. My matrix again was, where did you get them? My matrix was 2, -5, 2, 1. So I'm doing 2, -5, 2, 1 times the vector I hope to find. Let's call it v1, v2. I don't know. You can call it whatever you want. Equal to, because where it's going to be really not pretty. I think you can also, I think there's a similar, basically they're opposite signs. As in, so you could either say if the upper right corner is negative, then it'll be counterclockwise, or you could say if the lower left corner is positive, it'll be counterclockwise. These always have to be opposite signs when you have a spiral. He says, not super confidently. Right. Yeah, it always has to be like that. Right. These have to be opposite signs because you want the whole determinant to be positive. If these are the same signs, I mean, I guess you could do it. Anyway. Yeah. So this is going to equal 3 plus I root 39 over 2 times v1, v2. This seems pretty gross. So let's see what happens. Let's use the, I kind of feel like I want to use the second equation just because, I don't know, looks less terrible kind of. Let's use the second equation. So 2 times v1 plus v2, no, yeah, that's fine, equals 3 plus I root 39 over 2 times v2. So then I'm going to I'm going to subtract this over. So 2v1 equals 3 plus I root 39 over 2v2 minus 2v2 over 2, right? Instead of doing v2, I'm going to do 2v2 over 2. It's going to make a common denominator. Let's multiply everything by 2. So 4v1 equals 3 plus I root 39 v2 minus 2v2. 3 minus 2 is just 1. So 4v1 equals 1 plus I root 39 v2. And then finally, v1 is that divided by 4. So the eigenvector here could be, and there's lots of right answers. The eigenvector, one right answer would be saying that v2 is 1 and v1 is 1 plus I root 39 over 4. Terrible. I will point out that if we had used the first equation, so if we had done it as 2v1 minus 5v2 equal to 3 plus I root 39 all over 2 times v1, you'll probably get an answer that looks different. Let's do this a little bit more easily. I would probably start everything by multiplying both sides by 2. So 4v1 minus 10v2 equals 3 plus I root 39 v1. Subtract the 4v1, so negative 10v2, 3v1, right? So you can subtract the real part. So 3 minus 4 is negative 1 plus I root 39 v1, and then divide by negative 10, so that v2 is equal to positive 1 minus I root 39 all over 10 v1. So an alternative eigenvector here would be that v1 is 1 and v2 is 1 minus I root 39 over 10. Pretty gross. Are these the same? No. Are they multiples of each other? As long as I didn't make a mistake? Yes. Right? And so that's the thing. Eigenvectors, any multiple of an eigenvector, whether it's a real or a complex multiple, is also an eigenvector. So if you multiply this by 1 minus I root 39 over 10, you should end up getting that. Okay. We're not going to sweat it too much though. Let's find the second eigenvector. Let's do it the other way to see if it maybe sucks less. So now here's something that's worth noticing. Typically, when you find eigenvectors for complex eigenvalues, they're very similar to each other. They usually, like, I would not be surprised if our eigenvector for the next one is something like 1 and 1 plus I root 39 over 10. Usually the components are similar, but conjugate pairs as well. So, right, and actually that should, so here's the thing, if you've done it one way, doing it the other way is going to be real, right? Finding the other one is super easy. Because let's say we did this, but we changed it to, instead of being 3 plus I root 39, now it's 3 minus I root 39. So then that becomes plus, yeah. So here's the thing. Eigenvectors come in conjugate pairs as well. The real part just stays the same. The imaginary part changes signs. So the nice thing about finding the eigenvectors for the complex eigenvalues is you kind of only have to do it once. You can literally do it as plus or minus. I'm still going to so actually we'll do it the other way for another example. How about that? So we could write the general solution here. I don't really want to, but we can. So, so my general solution, x of t, y of t, would be c1 e to the, my lambda one was the positive one, so it would be, I think that would be viable, Ethan, right? Like there's no reason it's not true, right? That I'm solving this. Yeah, so I'll be a little bit more careful in my next example, but yes, I think that would be viable. So you have c1 e to the lambda one, which is the positive one. So it's 3 plus I root 39 over 2 times t times v1, which was the first one we did, which had the negative sign there. These just get so messy. And then plus c2 e to the 3 minus I root 39 over 2 times t times v2, which would be 1 and then 1 plus I root 39 over 10. Whew. Okay. I don't know for sure, but I really can't say. I would like to imagine that you won't be asked to find complex eigenvectors on the exam. It's usually a little bit, I don't want to say beyond the scope of the class. It's just usually kind of not what we care so much about testing on. But let's do another example. So let's say we've got this matrix here. So I've got A equal to the matrix 2, -3, 5, -2. And let me talk about just for a minute how I know what the solutions are going to look like without doing any work really at all. The trace, okay, so the trace is 0. The determinant is, let's see, -4 minus -3 times 5 is -15. My determinant's 11. So I know that since my trace is positive, I either have a node or a spiral, right? Again, looking at that picture that I showed you guys before, let me show you again just to remind everybody, right? If your determinant's negative, you have a saddle, you're done. If your determinant's positive, it could be any one of these 5 things. So my determinant's positive and my trace is 0. But the trace being 0 means I'm not left or right. It means I'm on this vertical axis. So I know I'm going to have a center. I'm going to have a neutral spiral. I didn't even find the eigenvalues, and I already knew I'm going to have a neutral spiral. It's kind of cool. Let's go ahead and find the eigenvalues. So the eigenvalues should be purely imaginary based on the trace being 0 here. My eigenvalue should be the trace plus or minus the square root of the trace squared minus 4 times the determinant all over 2, which is going to be just so this is one where we probably did too much work doing it this way, but it's going to be plus or minus the square root of negative 44 over 2, which is plus or minus the square root of 44. We can say it is 2 times the square root of 11. So it's plus or minus 2 times I times the square root of 11 all over 2. 2's cancel. So we get plus or minus I root 11 as your eigenvalues. It probably would have been easier to do it the other way, right? If we do it the other way, we have, a minus lambda and a minus lambda, and we get 2 minus lambda times negative 2 minus lambda minus negative 3 times 5. And then we end up getting, let's see, so this is going to be a negative 4, and then we're going to get a plus 2 lambda and a minus 2 lambda, which cancel out. Then we're going to get plus lambda squared, and then plus 15. So I've got lambda squared plus 11 equal to 0. Oh yeah, we know how to solve that without the quadratic formula. That's lambda squared equals negative 11. Lambda is plus or minus the square root of negative 11, which is I. So the trace determinant method isn't so much great for finding the eigenvalues. Like, it's usually pretty easy to do it this way. But what the trace determinant method is really great for is if you don't want to find the eigenvalues or the eigenvectors, and you just want to classify whether you have a saddle, a stable node, an unstable spiral, a stable spiral, or a neutral spiral, you can determine all of that based just on what the trace and the determinants are. End of story. Which is kind of cool. Okay, so looking at this one, let's go ahead and find the eigenvector. Eigenvectors. Actually, I should, before we find the eigenvectors, let's find the eigenvectors. So let's do it, and I'm going to try and do it the other way using the plus or minus. So I'm going to say that my eigenvalue, I'm just going to go straight with it's plus or minus I root 11. And I'm going to try the other way. So where I do the other way. Sure. So A minus lambda I times X equal to 0. So I'm doing A minus my eigenvalue. So I'm going to do 2 minus plus or minus I root 11 minus 3, 5, and then negative 2 minus plus or minus I root 11. I will say doing it this way feels like it's going to make a mistake. It feels like it's very, very plausible that we would make an error. So what I would probably suggest doing is not writing the plus or minus until the end. So I'm going to do a plus here for now. And then we will leave room to be like, okay, I'm just going to throw in a minus at the end and a minus at my answer as well. So let's see. So, looks terrible. I do think already off the bat, I do think this method's a little easier, because here's what my first equation is going to look like. I'm going to get 2 minus I root 11 times X minus 3Y equal to 0. That's real easy to isolate Y. There isn't another X or Y that I have to add to something else. So I think probably using this equation is the easier way to find complex eigenvectors. Let's go ahead and isolate Y. I'm going to get, let's just cut to the chase. I'm going to add 3Y over here, and then I'm going to divide by 3. So Y is going to equal 2 minus I root 11 divided by 3 times X. So my eigenvector, so again, lambda 1 is 2 minus positive I root 11, and the eigenvector for that is going to be X can be 1, and Y is going to be 2 minus I root 11 over 3. And now for the magic, if this was negative, this would also be negative. But if this was negative, then I'd have 2 minus a minus, so that would be positive. That would be positive. That's it. So we can see that if lambda 2 is 2 plus positive I root 11. And I'm just, no, that's a dumb, what am I doing, James? Let's be extra super, what? Sorry, oh, I wrote something really stupid. Not really stupid, but like a little stupid. My eigenvalue wasn't 2 minus positive I root 11. My eigenvalue was just positive I root 11. Sorry about that. And the other eigenvalue here was negative I root 11. Sorry about that. So then the corresponding eigenvector v2 is going to be, well, right, if x is 1, y is going to be 2 plus I root 11 over 3. So this definitely feels like it's true all the time. I'm pretty sure it is. If you have found one eigenvector for a complex eigenvalue, the eigenvector for the other complex eigenvalue is the same, except you change all the signs on the imaginary parts. So everything that's real, the 1 here and the 2/3 there, is still the same, a 1 here and a 2/3 there. Everything that's imaginary, the negative I root 11 over 3, changes signs to positive I root 11 over 3. That's it. Totally works every time, I promise. Okay. The other thing I want to say is that this spiral, this neutral spiral, would also be counterclockwise. Because again, we have a negative up there. But if you don't like that, and I don't love it personally because it's hard to remember, I literally have a sticky note on my computer right there that says like spiral clockwise has a plus up here, counterclockwise has a minus up there. If you don't like that, yeah, right. It's like if you're not allowed notes, you really don't like that. If you are allowed notes, it's totally right a good thing to have on it. Like, okay, I know this. I still want to show my work though. And the way I'm going to show the work is I typically like to pick points like 1, 1. So if I've got 2, -3, 5, -2, right? That was the matrix I was looking at, right? Yeah. If I start, and again, right, we know that this means, we know that we have dx dt equals 2x minus 3y, and dy dt equals 5x minus 2y. I'm going to start trying to just, I usually like to pick these 4 points here. 1, 1, -1, 1, -1, -1, and 1, -1. I pick 1, 1. This is going to be 2 minus 3, which is 1. So it's going to be, right, so 1, 1, it's going to be over, and 1, 1, I'm going to get 3, it's going to be up. So it's going to be over and up. More up than over, right? It's 1 over, it's 3 up. And then at -1, 1, I'm going to get -2 minus 3, which is -5. So it's going to be going left, and -5 minus 2, which is going to be -7, so left and down. So over here, it's going to be going that way. And then I bet down here, it's going to be going that way. Let's find out though. So at -1, -1, I'm going to get -2 plus 3, which is +1, and -5. Well, in fact, things are opposite sides, right? If you've got 1, 1 is over 1 and up 3, -1, 1 is going to be left 1 and down 3. Yeah, that's right. It feels kind of wrong. Okay. So anyway, point -1, 1, I'm going to get -2 plus 3, which is 1. I made a mistake on the very first one. I'm like, so here's what I should be getting. I should be getting that the vector at -1, 1 is pointing the opposite direction this is going. When I'm plugging in -1 on -1, I'm getting -2 plus 3, which is to the right one, and -5 plus 2, which is down 3. It's kind of going like that. And the problem is, it should be pointing in the opposite direction this one is, which it isn't. And the reason it isn't is I made a mistake here. When I plugged in 1, 1, I should have gotten 2 minus 3, which is -1, pointing to the left. And then this one here should be the opposite direction that way. So you really only have to do 2 of them because the other 2 kind of already come out. But this is clearly going to be going that way. So my spiral, my neutral spiral goes that way. Not that way, James, that way. Cool. Let's see, what else can I say about this? In 2 minutes? Not a lot. So let me just say one more. Let me do a quick 2-minute plug for why the trace determinant method is worthwhile. So here's the deal. When you use the trace determinant method, right? And so let's say we have some matrix, I don't know what it is, 1, 2, 3, 4. I don't really care. The trace is 1 plus 4. The determinant is 4 minus 6. Okay. But then we use that to find the solutions using the quadratic formula, right? We're getting that the eigenvalues are the trace plus or minus the square root of the trace squared minus 4 times delta all over 2. The 2 doesn't really matter. I mean, it matters, but not really. So here's what we get. If the determinant is negative, here's what's going to happen. If the determinant is negative, tau squared minus a negative is going to be positive. If that's positive, you have a number plus or minus a positive number. And here's the thing. This number is going to be bigger than tau squared. And so the square root of this will be bigger than tau. So what you have if your determinant is negative, is you have tau plus or minus a real number that's bigger than tau, the trace, divided by 2. Well, a real number plus a number that's bigger than it. So if tau is positive, then if you add something to it that's bigger than it, it's going to be slightly positive. And if you subtract something bigger, it's going to be negative. If tau is negative and you add something that's bigger than it, and I should say really, this has to be positive because we're taking the square root of it. So if tau is negative, a negative plus a number that's bigger than it is going to be positive. So if your determinant's negative, you're always going to get opposite sign eigenvalues, which means you're always going to get a Saturn. On the other hand, if your determinant is positive, then there's a lot more work to do. Then it depends on what tau is. So if tau is positive, it's unstable. If tau is negative, it's stable. And then if tau squared is bigger than 4 delta, that means the insides of this is positive. That means you have a node. If tau squared is less than 4 delta, well, then your discriminant here is negative. You're taking the square root of a negative, which is going to be complex. That means you're going to have a spiral. So that's it. I know, I'm like, that's it. Okay. That's a lot to digest. But again, it's all kind of summed up in that picture I showed you guys a couple of times, which I'm going to show you one more time just for the fun of it. Here's that picture again. Oh, let me do one more thing. Yeah. So, right here you can see. Why do I always accidentally open iTunes? Stupid. Sorry. You can see here, right? Oh yeah, if your determinant's negative, you have to have a saddle. If your determinant's positive, well, then if your trace is positive, my mouse, come on, work, mouse. Sorry. If your trace is positive, you're either an unstable node or an unstable spiral. If your trace is negative, you're either a stable node or a stable spiral. And then if your trace is 0 and your determinant's positive, you're going to be a center or a neutral spiral. And then the only other determining factor is the inside of your square root positive or negative, right? If the inside's positive, great, you're a node because the determinant is less than 1/4 the trace squared. And if you're up here, you're a spiral because your determinant is bigger than 1/4 the trace squared, and the inside of this is negative.